You have been told the universe had a beginning. 13.8 billion years ago, everything that exists was packed into a single point, and then it expanded. And that expansion is what we call the Big Bang. There is no before. The question is supposed to be meaningless. You can say the words. They simply do not point at anything. This is the standard answer. It sits in every textbook and every documentary, and for most of the last 100 years, almost no serious physicist argued with it. One of the people who understands the geometry of that beginning better than almost anyone alive does not believe it. His name is Roger Penrose. In 2020, he was given the Nobel Prize in Physics for work he did decades earlier, proving that black holes are not a mathematical fluke, but something Einstein's equations genuinely demand. He has spent 60 years thinking about the shape of space and time, and somewhere in those 60 years, he became convinced that the Big Bang was not the start of everything. He thinks it was a doorway. On the far side of it, in his picture, sits another universe. Not a parallel one, not a branch, not a bubble drifting beside our own. An earlier one, a complete universe that formed, filled itself with stars and galaxies, grew old, and died in full before the first instant of ours. Penrose believes our Big Bang was that universe's ending, seen from the other side of the door. And here is the part that should keep you awake. He thinks it left a mark. There is a faint glow filling all of space, the oldest light there is, set loose when the universe was a few 100,000 years old and finally cool enough to turn transparent. We call it the cosmic microwave background. It is almost perfectly smooth, sitting everywhere at about 2.7 degrees above absolute zero. But scattered across that smoothness, Penrose says, are rings, small circular patches very slightly warmer than everything around them. He gave them a name, and that name is the thread we are going to follow all the way through tonight. He calls them Hawking points. A Hawking point, if it is real, is the last light of a dead universe. It is what is left when a giant black hole in the previous cosmos spends an almost unthinkable stretch of time slowly evaporating away until the very end, when it lets go of everything it ever swallowed in one final flash. That burst, Penrose argues, bleeds through the doorway and lands in our sky as a warm circular smudge in the background glow. A scar carried across the death of one universe and into the birth of the next. If you enjoy these long journeys into the strange and the cosmic, hit subscribe and settle in. This is a long one, and it is built to be slept through. Because in 2018, Penrose and 3 colleagues published a paper claiming they had actually found these scars in the real data at a confidence level of 99.98%. For a few weeks, the headlines said a previous universe had been detected. And then 2 physicists in Vancouver took the same data, ran the same search more carefully, and watched that number collapse until it meant almost nothing at all. We are going to walk all the way into that fight and into the stranger idea sitting underneath it. The idea that the end of a universe and its beginning might be the very same thing. To understand why a man like Roger Penrose would look at the most successful theory in the history of science and decide it was missing its first page, you have to understand what that theory actually says. Not the cartoon version, where everything detonates outward from a fixed spot in empty space, like a firework over a dark field. The real one. The version that took the better part of a century to build, assembled slowly by people who, for the most part, did not want the answer they kept arriving at. It begins with a problem nobody went looking for. In the early years of the 20th century, the universe was assumed to be static, eternal, unchanging on the largest scale. The stars had always been there, and always would be, the same sky over every generation that ever looked up. When Albert Einstein finished his theory of general relativity in 1915 and turned it loose on the universe as a whole, the equations refused to sit still. They wanted the universe to either expand or collapse. They would not let it simply hold its shape. Einstein was so unsettled by this that he added an extra term to his own equations, a kind of cosmic counterweight whose only job was to hold everything in place. He called it the cosmological constant. He later abandoned it, and there is a story, passed around for decades and probably polished in the retelling, that he came to regard it as the greatest blunder of his life. The equations had been trying to tell him something, and he had told them to be quiet. Other people listened. In 1922, a Russian mathematician named Alexander Friedmann worked through Einstein's equations without the counterweight and found a whole family of universes that grew or shrank over time. Some of them expanded forever. Some of them swelled and then collapsed. A few even bounced, expanding and contracting in an endless rhythm, an idea that will matter a great deal before tonight is over. Friedmann did not live to see any of it confirmed. He died in 1925, only 37 years old, of typhoid fever, years before the telescopes caught up to his mathematics. The man who first saw the expanding universe inside Einstein's equations never knew he was right. A few years later, working separately and apparently unaware of Friedmann's results, a Belgian named Georges Lemaitre arrived at the same place by a different road. Lemaitre was both a trained physicist and an ordained Catholic priest, which gave the press a tidy story it never quite let go of. He went further than Friedmann. If the universe is expanding, he reasoned, then run the film backward. Yesterday, it was smaller. 1 billion years ago, smaller still. Push it back far enough, and everything you can see, every galaxy and every atom, converges toward a single dense seed. He called it the primeval atom, the cosmic egg. When Lemaitre first described the idea to Einstein, the great man was unimpressed. Einstein is said to have told him that his calculations were correct, but his physics was abominable. Einstein had spent years teaching his equations to sit still, and here was a priest insisting they wanted to run. And then the sky confirmed it. In 1929, the American astronomer Edwin Hubble, working with the 100-inch telescope at Mount Wilson, measured the light from dozens of distant galaxies and found that nearly all of them were rushing away from us. Not only that, the farther away a galaxy sat, the faster it fled. That is exactly the pattern you would see if the entire fabric of space were stretching, carrying the galaxies apart like raisins set into a rising loaf of bread. 3 people working in 3 different ways, from pure mathematics and from physics and from raw observation, had walked into the same impossible room. The universe had a size that changed, and if it was bigger today than yesterday, then it had a yesterday it could be traced back to. Trace it back far enough, and you reach a moment when everything that exists was compressed into a state of impossible density and impossible heat. The age of that moment, measured with extraordinary care over the decades since, is 13.8 billion years. That number is so large, it stops meaning anything. So let me hand you a way to hold it. Imagine the entire history of the universe pressed into a single calendar year, the Big Bang, at the 1st second of January the 1st. On that calendar, the dinosaurs do not appear until the day after Christmas. Every word ever written by a human being, every empire, every person you have ever loved or read about, fits inside the last few seconds before midnight on the 31st of December. The Big Bang is not just old, it is the floor under all of time. But a theory this strange needed proof you could touch, and for a while it had a serious rival that offered none of this drama. Through the 1940s and 50s, a group of brilliant physicists led by Fred Hoyle, working with Hermann Bondi and Thomas Gold, championed a different picture entirely. They called it the steady-state universe. Yes, space was expanding, they agreed, but there had been no beginning. As the galaxies drew apart, new matter was quietly created in the gaps, just enough to keep the overall density of the cosmos constant forever. No birth, no death, no first moment. An eternal, self-renewing universe with no awkward questions about what came before. It was elegant, and many serious people preferred it. Hoyle, in particular, found the idea of a single explosive origin almost distasteful, and during a radio broadcast in 1949, he reached for a dismissive phrase to describe the rival theory. He called it this Big Bang idea. The name was meant to belittle it. Instead, it stuck, and the theory Hoyle was mocking is the one your textbooks teach today, under the label he gave it as an insult. What settled the argument was a discovery made by two engineers who were not looking for it. Their names were Arno Penzias and Robert Wilson, and in 1965 they were working at Bell Labs in Holmdel, New Jersey, trying to tune a large horn-shaped antenna for satellite communication. They kept running into a faint hiss, a low, steady static that came from every direction in the sky at once, day and night, no matter where they pointed the instrument. They checked their equipment. They cooled their detectors. They even climbed inside the antenna and scrubbed out the droppings left by a pair of pigeons that had been roosting there, a substance Penzias described in the politest possible terms in his note. The hiss would not go away. It was not the pigeons. It was not the machine. It was the sky itself. What they had stumbled into was the single most important sound in cosmology, and they very nearly threw it away as noise. Decades earlier, the physicist George Gamow and his colleagues Ralph Alpha and Robert Herman had predicted that if the universe really did begin in a hot, dense state, that early fire should still be glowing faintly today, stretched by the expansion of space into a whisper of microwave radiation filling everything. A separate team at Princeton, led by Robert Dick, was building an instrument to go looking for exactly that signal when they heard, through a phone call, that two engineers an hour up the road had already found it without meaning to. Penzias and Wilson received the Nobel Prize for it in 1978. They had recorded the afterglow of creation and mistaken it for a problem with the wiring. And the steady-state universe, which had no way to produce such a glow, quietly died. There had been a hot beginning after all. We call that glow the cosmic microwave background, and it is the oldest light in existence. It was set free when the universe was roughly 380,000 years old, the moment when the cooling cosmos finally let its particles settle into atoms and turn transparent for the first time, releasing the light that had been trapped inside it. That light has been traveling ever since, for almost the entire age of the universe, before ending its journey in the dish of an antenna or, increasingly, in the sensors of a spacecraft. It sits today at 2.725 degrees above absolute zero, the faintest warmth left over from the hottest event there ever was. Over the following decades, we learned to read that light with almost unbelievable precision. A satellite called COBE, launched in 1989, showed that the background matched the predicted glow of a perfect cooling object to a degree that made the audience at one physics conference burst into applause. It also revealed something subtler. The glow is not perfectly even. There are tiny ripples in it, regions 100,000th of a degree warmer or cooler than their surroundings. Those faint ripples are the most consequential blemishes in the universe because they are the seeds. The slightly denser patches pulled in more matter by gravity, and over billions of years they grew into the galaxies, the stars, and eventually the planet you are lying on. The two scientists who led that mission, John Mather and George Smoot, won the Nobel Prize for it in 2006. Later missions, WMAP and then the European Planck satellite, mapped those ripples in finer and finer detail, and it was their measurements that pinned the age of the universe to 13.8 billion years and showed that space, on the largest scales we can survey, is geometrically flat. Sit for a moment with how astonishing that precision is, because it is the only reason any of the rest of tonight is even testable. The Planck satellite did its work from a point in space roughly 1 million miles from Earth, a quiet gravitational parking spot where it could turn its back on the sun and our planet and stare into the cold dark without interference. From there, it scanned the entire sky, over and over, measuring the temperature of the oldest light to within millionths of a degree. Think about what that actually means. It mapped the faint, leftover warmth of the Big Bang across the whole of the heavens and could tell that one patch of sky was a few millionths of a degree warmer than the patch right beside it. Without that almost absurd delicacy, the warm rings Penrose would later go hunting for would be utterly invisible, lost in the blur of any cruder instrument. The entire argument over whether a previous universe left a mark on our sky is only possible because we have learned, within a single human lifetime, to read that sky with a care that would once have sounded like fantasy. So that is the established picture, and I want to be fair to it, because it is genuinely one of the great achievements of the human mind. A hot, dense beginning, an expanding space, a relic glow you can still measure in your own backyard with the right equipment. It hangs together with a precision that should not be possible for a guess about the first moments of everything. And inside that picture, the question this whole video is built around is not just hard to answer, it is supposed to be forbidden. What came before the Big Bang? Stephen Hawking had a favorite way of shutting the question down. Asking what happened before the Big Bang, he said, is like asking what lies south of the South Pole. You can form the sentence, you can say the words out loud, but there is no place the words describe, because the South Pole is where south runs out. In the standard picture, the Big Bang is not an event that happened inside time. It is the edge of time. Time itself begins there. There is no earlier moment for a before to live in, because moments themselves only start once the clock has been wound. The question dissolves in your hand the moment you try to hold it. For most of a century, that was the end of the conversation. A sensible cosmologist learned not to ask. But there was always a loose thread hanging off the edge of the theory, and a small number of people could never stop staring at it. The thread has to do with time, and with the strange fact that it only ever runs one way. You know this in your body, even if you have never put it into words. A cup falls from a table and shatters on the floor, but you have never once seen the pieces leap up and reassemble into a cup. Heat flows from your warm coffee into the cold room until both are the same temperature. never the other way around. The English astronomer Arthur Eddington gave this one-way flow a name in the 1920s. He called it the arrow of time, and he argued it was the most fundamental fact about the universe we know. The deeper foundation underneath it is the second law of thermodynamics, an idea with a long and somber history. The German physicist Rudolf Clausius, who coined the word entropy in 1865, summed the whole law up in a single grim sentence. The energy of the universe is constant. The entropy of the universe tends toward a maximum. Translated, that means disorder always wins in the end. It was the Austrian physicist Ludwig Boltzmann who explained why, by showing that entropy is really a measure of how many ways the pieces of a system can be rearranged without your noticing the difference. A shattered cup can be arranged in countless ways and still look like a mess. An intact cup can only be arranged in a very few. Disorder is simply overwhelmingly more likely than order, so left to itself, the universe drifts from the rare and ordered toward the common and disordered, and never back. Boltzmann paid a terrible price for being right too early. His ideas were ridiculed by powerful contemporaries who did not believe in atoms at all, and in 1906, in poor health and deep depression, he took his own life. The equation that captures his great insight, relating entropy to the number of possible arrangements, is carved on his tombstone in Vienna. He never knew it would become one of the load-bearing walls of modern physics. Here is where it gets strange, and here is the thread Penrose could not leave alone. If the universe has been getting messier and more disordered every second since it began, then run that backward, the way Lemaitre ran the expansion backward. It means the universe must have started in a state of staggering order, almost perfect order. The lowest entropy the cosmos has ever had, or ever will have, was right there at the very beginning, in the fire of the Big Bang itself. And that is deeply odd, because a hot, dense explosion is the last place you would expect to find exquisite order. A bomb does not produce a tidy room. Yet the early universe, as the cosmic background light shows us in detail, was almost flawlessly smooth and uniform, the same in every direction to within that one part in 100,000. The beginning of everything was not chaos. It was the most finely ordered state the universe has ever known, and nothing in the standard theory explains why. Penrose gave this puzzle a precise shape. Back in 1979, in a paper on singularities and the asymmetry of time, he proposed what he called the Weyl curvature hypothesis. The mathematics underneath it is heavy, but the idea you can hold. The curvature of space-time comes in two parts. One part, named after the mathematician Gregorio Ricci, responds directly to the matter sitting in a region. The other part, named after Hermann Weyl, describes the free-roaming side of gravity, the tidal stretching and squeezing that travels through empty space and lets matter clump together into structures. Penrose's insight was that gravitational entropy, the disorder hidden in how matter is clumped, lives in that wheel part. A smooth, evenly spread universe has almost no Weyl curvature and very low gravitational entropy. A universe full of dense clumps, and especially full of black holes, has enormous Weyl curvature and enormous entropy. His hypothesis was that at the Big Bang, this Weyl curvature was forced down to essentially zero. The beginning was geometrically smooth in a very specific, very demanding way. That smoothness is the source of the low entropy. It is the reason there is an arrow of time at all. But notice what Penrose had really done. He had not explained the special beginning. He had only named the condition that had to be true for our universe to make sense and stamped it onto the first instant by hand. Why should the universe start in such an absurdly ordered, smooth, low-entropy state when there were so many more disordered ways for it to have begun? The standard answer, when anyone gave one, was a shrug. It just did. Those were the initial conditions. You do not get to ask where the initial conditions came from, any more than you get to ask what lies south of the South Pole. And Penrose, staring at that smooth and orderly beginning, noticed something that almost everyone else had filed away as a coincidence. He looked at the far future of the universe, at the cold and empty state it is slowly drifting toward after all the stars have died, and he realized it had the same shape, smooth, featureless, low in that same whale curvature. The beginning of time and the end of time, when you stripped away everything else and wrote them out in the bare language of geometry, were starting to look like the same place. Most cosmologists glanced at that resemblance and looked away, the way you look away from a face in the wallpaper. Penrose looked harder, and what he saw on the other side of that resemblance is where this story stops being textbook physics and becomes something much stranger. The resemblance is not a coincidence. That is the claim. And to see why a careful mind like Penrose would take something so wild seriously, you have to ask a question that sounds almost childish until you try to answer it. How do you measure the size of the universe? Not in practice, with telescopes and redshifts. In principle. What does it even mean to say the universe is large or small, or that it has a size at all? Think about what you actually do when you measure anything. You lay something of known length against the thing you want to measure, a ruler against a table, a wavelength of light against an atom. Measurement is always a comparison between two things, and at least one of them has to be a fixed standard you can trust to stay the same. Now ask where that fixed standard comes from. In the end, every ruler we have ever built bottoms out in the masses of the particles that make it up, the size of an atom, the length of a chemical bond, the tick of an atomic clock. All of it is set by the mass of the electron and the other fundamental constants. Mass is what gives the universe a built-in sense of scale. Take away mass, and you have taken away every ruler in existence at once. This is the part of Penrose's thinking that I find genuinely beautiful, and it leans on two of the most famous equations in physics, sitting quietly next to each other. The first is Einstein's, the one everyone can recite. Energy equals mass times the speed of light squared. It says mass is a form of energy. The second comes from quantum mechanics. The energy of a particle is proportional to its frequency, to how fast its associated wave oscillates. Put those two side by side, and something strange falls out. If mass is energy, and energy is frequency, then mass is a kind of frequency. Every massive particle has a natural rhythm built into it, an internal oscillation, a tiny clock ticking away at a rate fixed by how much mass it carries. A particle with mass keeps time. That is what it means, at the deepest level, to have mass. You become a clock. And here is the consequence. A particle with no mass has no clock. The clearest example is the photon, the particle of light, which has no rest mass at all. A photon does not experience the passage of time. It has no internal rhythm, no way to register a before and an after. From the photon's own point of view, the instant it is created and the instant it is absorbed, billions of years and billions of light years apart in our terms, are the same instant. Light does not age. A massless particle is, in a precise physical sense, blind to both time and scale. It cannot tell you how big the universe is, because it has no ruler. It cannot tell you how old the universe is, because it has no clock. Now hold that thought, and let us walk all the way to the end of time. The far future of the universe is not a fiery collapse. The current evidence points the other way. And how we learn that turns out to matter enormously for Penrose's story. In 1998, two competing teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, set out to measure how fast the expansion of the universe was slowing down. Everyone assumed gravity must be putting on the brakes. Instead, they found the opposite. The expansion is speeding up. Some unknown influence, which we now call dark energy, is pushing space apart faster and faster. The discovery won the three of them the Nobel Prize in 2011, and it rewrote the long-term forecast for the cosmos. The universe is not heading for a crunch. It is heading for a runaway, ever-accelerating emptiness. Hold on to that fact, because in a strange twist, it is exactly what Penrose's theory needs to work. So the long-term forecast is not a collapse. It is a slow, cold, deepening loneliness. The stars are burning through their fuel. New stars will keep forming for a while, but the gas runs out eventually, and the last stars will gutter and die. Some unimaginable stretch of time from now, the sky goes dark for good. What remains is debris. Dead stars, cold planets, drifting gas, and the great gravitational drains at the centers of galaxies, the black holes. And then, slowly, even the black holes go. This is one of Stephen Hawking's most important discoveries, the one his name is tied to in this story. Back in 1974, he showed that black holes are not perfectly black. Through a subtle quantum effect right at their edges, where pairs of particles flicker in and out of existence, one of each pair can slip away, while the other falls in. And the result is that a black hole leaks the faintest possible trickle of radiation, losing a sliver of mass with every escape. A black hole slowly evaporates. The strange thing is that the smaller a black hole gets, the hotter and faster it radiates, so the process runs away at the very end, finishing in one last violent burst. For a giant black hole, the kind that anchors a galaxy, the whole process is almost incomprehensibly slow. A supermassive black hole takes something on the order of 10 to the 100th power years to fully evaporate. That is a 1 followed by 100 zeros. To feel how empty that number is, consider that the entire age of the universe so far, 13.8 billion years, is so much smaller than a Google of years that if you shrank the whole life of the cosmos to the width of a single atom, the lifespan of one of these black holes would still stretch out vastly farther than the size of the observable universe. The black holes are the last things to leave. They are the universe's final candles, and they burn down to nothing across a span of time that makes the present age of everything look like less than a rounding error. Slow down on those final moments, because they are where the Hawking points are born. For nearly all of its existence, a supermassive black hole is colder than the thin space around it, leaking almost nothing, a slow drip across the dark. Only in its last stretch does it heat and brighten and finish in a burst, the closest thing the dying universe has to an explosion, the final unspooling of everything that black hole ever swallowed, let go in one last release of radiation. The timescales are the kind that break the mind. A black hole the mass of our sun would take something like 10 to the 67th years to evaporate, and the giants at the centers of galaxies, millions or billions of times heavier, take that full Google of years we just tried and failed to picture. When the final black hole flickers out, the cosmos has nothing left that can change, and it is precisely that last flash, that ultimate release of a black hole's hoarded energy, that Penrose says gets stamped onto the next universe as a warm ring. A Hawking point is a death certificate written in light for the largest thing a universe can build. When the last black hole has finished evaporating, what is left? Photons. Stray particles of light drifting through an endlessly expanding dark. A few other massless ripples. And the dark energy, still pushing space apart, faster all the time. Which is why this matters. Because dark energy guarantees that the far future is not just empty, but ever more thinly stretched, an exponentially expanding cold, smooth nothingness with no edge and no feature. That is the final state of the universe in the standard picture. A cold, thin, massless soup spread across an emptiness that keeps on growing forever. It is, frankly, the bleakest ending in all of science. Heat, death. The universe does not end with a bang or even a whimper. It ends with a fade, and then nothing changes ever again, because there is nothing left to change. Except, look at what that final state is actually made of. It is a universe with no mass in it. And we just established what a universe with no mass cannot do. It cannot measure time because there are no clocks left, no massive particles ticking out a rhythm. It cannot measure size because there are no rulers left, no fixed standard of length anywhere in it. The far future universe is unthinkably enormous and unthinkably cold by our reckoning. But there is nothing inside it that could ever know that. To the only things that remain, the photons that feel no time and measure no distance, the words enormous and cold and old have no meaning. The information that the universe is large has been erased because everything capable of registering largeness is gone. This is the hinge of the whole idea, so let me say it plainly. If nothing in the far future can tell the difference between vast and tiny, between ancient and newborn, then for all physical purposes, there is no difference. A universe that has forgotten its own scale is no longer distinguishable from a universe that has no scale yet. And a universe with no scale yet, infinitely dense by our standards, but unable to know it, hot beyond reckoning, but with nothing inside to feel the heat, is exactly what the Big Bang is. The cold dead end and the hot violent beginning are not similar. In the mathematics, once you discard the scale that neither of them can measure, they are the same state. Geometers have a word for this kind of relationship. They call it conformal. A conformal map keeps all the angles intact while throwing the absolute sizes away. Under that lens, the frozen graveyard at the end of time and the blazing seed at the start of time become two descriptions of one identical thing. If that sounds too abstract to picture, there is a way in, and it runs through one of the strangest friendships in 20th century science. In 1954, a young Penrose, still a graduate student, attended a mathematics conference in Amsterdam and wandered almost by accident into an exhibition of work by the Dutch artist Maurits Escher. He was transfixed. Escher drew impossible things, staircases that climbed forever and returned to where they began, water that flowed uphill into the pool it had just fallen from, worlds that folded against the ordinary rules of space. Penrose went home and, working with his father Lionel, dreamed up impossible objects of his own, the famous Penrose triangle and the endless Penrose staircase, and sent them to Escher, who turned them into two of his most celebrated prints. The mathematician and the artist had found the same obsession from opposite directions. How do you fit something impossible, something infinite, onto an ordinary flat page? And that question is the secret to conformal geometry. Look at Escher's circle limit prints, the ones filled with angels and devils or with little fish repeating outward toward a circular boundary. As the figures approach the rim, they shrink, smaller and smaller, packing an endless number of them into a finite circle. But here is the trick. Their angles never change. Each angel is the same shape as the last, no matter how small it gets near the edge. The sizes are crushed to nothing at the boundary, while the shapes are preserved perfectly. That is exactly what a conformal map does. It is allowed to stretch and shrink as wildly as it likes, growing things at the center and squeezing them at the edge, as long as it never bends an angle. Escher's circle holds an actual infinity inside a line you can draw with a compass, an unending tiling pressed into a finite disk, the whole boundless plane tamed onto a sheet of paper. This is the move Penrose spent his career turning into physics. If you can squeeze an infinite plane onto a finite disk by shrinking things near the edge, then you can squeeze the infinite future of a universe onto a finite boundary by precisely the same sleight of hand. The cold, endless, ever-expanding far future, which by ordinary reckoning trails off into forever, becomes in conformal terms a clean, definite edge, the rim of Escher's circle. And once the end of time is a clean edge rather than a fog, you can ask the one question no one else could even phrase. What is on the other side of the rim? In Escher's prints, the answer was always more tiling, more angels and devils pressing in from beyond the boundary. In Penrose's cosmology, the answer is another universe pressing in from beyond the end of time. Conformal cyclic cosmology is, in a real sense, Escher's circle limit applied to time itself, the boundary of one finished world becoming the first bright instant of the next. And here is where Penrose had an advantage almost no one else possessed, because he had spent his career building exactly the right tool for this. Back in the 1960s, he had invented a way of drawing entire universes on a single finite page, squashing the infinite reaches of space and time inward, so that even the farthest future and the most distant edges could be sketched as ordinary lines and points. Physicists call them Penrose diagrams, and they are the standard way the whole field now visualizes the structure of space-time, including its boundaries. On such a diagram, the infinite far future of an expanding universe is not a vague haze trailing off the edge. It becomes a clean, definite surface, a smooth boundary you can draw and study. Penrose had spent decades looking at that future boundary, so when he asked whether it might be glued to something, he was not speaking loosely. He had a precise, geometric picture of the surface he wanted to attach. And who this man actually is sharpens the strangeness of what he is claiming. In 1965, the same year Penzias and Wilson stumbled onto the afterglow of the Big Bang, Roger Penrose, then in his early 30s, published a short paper that would eventually win him the Nobel Prize more than half a century later. In it, he introduced a new idea he called a trapped surface, and he used it to prove something that had haunted and divided physicists for decades. When a heavy enough lump of matter collapses under its own gravity, the formation of a singularity, a place where the smooth fabric of space-time tears and the equations give out, is not a fragile accident of perfectly round idealized calculations. It is unavoidable. Before Penrose, many had hoped that real, lumpy, imperfect collapse would somehow swerve around the singularity. He showed, with geometry alone, that it cannot. The breakdown of space-time at the heart of a black hole is a robust prediction of Einstein's own theory. A few years later, in 1970, working with a young Stephen Hawking, Penrose turned the same mathematical machinery around and aimed it at the past. Run the expanding universe backward, the two of them showed, and it too must terminate in a singularity, a first moment where the equations fail. In other words, the Big Bang. The Penrose-Hawking singularity theorems are a large part of the reason your textbooks speak of the Big Bang as a genuine beginning at all, a true edge of time with the equations breaking down behind it. When the Nobel Committee honored Penrose in 2020, it was for exactly this, for the discovery that black hole formation and the singularities that come with it are a robust prediction of general relativity. So hold the shape of this for a moment, because it is almost unbearably poignant. The man who, more than anyone alive, proved that the Big Bang must be a true singularity, a hard and final edge of space-time, is the same man who now spends his days insisting that it is not an edge at all, that it is a doorway. He is, in the most literal sense, arguing against his younger self. He built the wall as a young theorist, with a rigor no one could break, and he has spent his old age trying to show there is something on the far side of it. That is not the trajectory of a crank chasing a fantasy. It is the trajectory of someone who took the wall more seriously than anyone else ever has, lived alongside it for 50 years, and slowly became convinced he could see a way through. Whether or not he is right, a life like that earns the question. This was the leap Penrose made, somewhere around the year 2005, in what he himself cheerfully called an outrageous suggestion. If the end of one universe is conformally identical to the beginning of another, then why not simply connect them? Take the smooth, scaleless, far future boundary of a dead universe and glue it directly onto the smooth, scaleless Big Bang of a fresh one. The death of the old becomes the birth of the new, not metaphorically, but as a literal joining of two geometries across a shared surface. And notice why dark energy turns out to be essential here. It is the accelerating expansion that smooths the far future into the clean, well-behaved boundary the gluing requires. Without dark energy, the future would be a ragged, ambiguous place, and there would be nothing tidy to attach. The very thing that makes our cosmic future so bleak is the thing that lets it become a doorway. Penrose gave each of these complete cycles a name borrowed from the deep past. He called them Aeons. Our universe, in his picture, is a single aeon in an endless chain of them, stretching backward forever and forward forever, each one ending in a cold, massless fade that the next one experiences as a hot, dense dawn. He named the whole framework Conformal Cyclic Cosmology, and in its simplest form, it is almost austere, just an expanding universe full of radiation and dark energy, stripped down until the mathematics of the end and the beginning can be made to meet. And look what it does to the puzzle we left hanging. Remember the thing that had no explanation in the standard picture, the strange, almost suspicious smoothness of our Big Bang, the exquisite low-entropy order at the start of time that the wheel curvature hypothesis could describe but never justify, the order that had to be stamped on by hand. In conformal cyclic cosmology, that mystery dissolves. Our beginning was smooth because it inherited the smoothness of the previous aeon's end. The orderly, featureless state our universe started in is simply what a dead universe looks like after it has finished spreading itself thin across infinity. The pristine condition of our Big Bang is not a coincidence the universe was lucky to be born with. It is a hand-me-down. The tidy, low-entropy beginning we could never explain is the cold, smoothed-out corpse of the universe that came before. That is the sense in which Penrose thinks the Big Bang was a doorway rather than a wall. On the far side of it is not nothing. On the far side is the long, quiet death of someone else's cosmos. And follow that thread one step further, because it leads somewhere genuinely vertiginous. The reason time runs forward in our universe, the reason your coffee cools and the dropped cup shatters and never leaps back together, the reason you remember the past and not the future, all of it traces back to that smooth, ordered beginning. The arrow of time points away from the Big Bang because the Big Bang was the most ordered moment there will ever be, and everything since has been the slow slide into disorder. But in Penrose's picture, that order was never ours to begin with. We inherited it, which means the arrow of time in our universe was set by the death of the previous one. The plain fact that there is a difference between before and after, that your life runs one way and cannot be rewound, is a hand-me-down from a cosmos you will never see. The previous Aeon did not only seed our galaxies, it pointed our clocks. Every irreversible thing that has ever happened to you, every memory you carry forward and can never carry back, runs in the direction it does because of the particular way a universe before yours chose to end. It is an extraordinary story, and a strange comfort lives inside it. But a beautiful idea is worth nothing in physics unless it leaves a mark you can go and check. Eternal inflation, the rival picture that imagines our universe as one bubble among endless others, has long been criticized for predicting almost nothing testable, for floating just out of reach of any experiment. Penrose knew his theory would die the same death if it could only tell pretty stories. So he asked the hard question: if there really was an Aeon before ours, what would it have left behind that we could still find today, written somewhere we already know how to read? His answer brings us back to the word planted at the very start of tonight: Hawking points. Think again about the death of the previous Aeon. Across its long life, that universe would have built its own galaxies, and at the heart of each galaxy, a supermassive black hole. Over the unthinkable stretch toward its heat death, those black holes would have swallowed nearly everything, and then, one by one, evaporated away by Hawking's slow leak, each releasing across its entire lifetime the equivalent of an enormous, concentrated outpourings of energy. Now run that through the conformal crossover. All the energy a single giant black hole pours out over a googol years gets compressed at the join between aeons onto effectively a single point in the newborn universe. That point sits in the sky of the next Aeon as a small, intense, concentrated source. As the young universe expands, that source should bloom outward into a circular patch in the background glow, a region very slightly warmer than its surroundings, ringed and concentric, a fossil of a black hole that died in a universe before this one. Penrose predicted that our cosmic microwave background should be freckled with these warm circles. He called them Hawking points, because each one is the echo of Hawking radiation from a cosmos that no longer exists. And then, in 2018, he and 3 colleagues went looking. Daniel Ahn, Christoph Meissner, Paweł Nurowski, and Penrose himself took the high-precision maps of the cosmic background and ran a search for exactly these features. They published a paper with a title that sounds almost cautious until you read what is inside it. Apparent evidence for Hawking points in the cosmic microwave background sky. In it, they claim they had found the warm, circular regions the theory predicted, and not at the level of a hopeful hint. They reported a confidence of 99.98% that what they were seeing was a real feature of the data rather than random chance. For a few weeks, parts of the press ran with the obvious headline, "A previous universe had been detected. Scientists had seen through the doorway." Be honest about what that number, 99.98%, actually meant, because figures like it have a hypnotic power. It did not mean there was a 99.98% chance that a previous universe exists. It is easy to hear it that way, and much of the coverage effectively did. What it meant was narrower and far more slippery. It meant that, by the particular measure the team had chosen, a signal this strong should turn up in only about 2 out of every 10,000 random skies that contain no such points at all. That sounds overwhelming. But everything hangs on whether those fake skies were honest stand-ins for the real one, and on whether the search had quietly handed itself many chances to find something. The quality of the simulations and the breadth of the hunt. Those two questions are exactly where the earlier claim had come apart. So the high number did not reassure the specialist. It put them on guard. A confidence of 99.98% in a field this delicate is not a trophy. It is a flag that says check this very carefully, because either something remarkable is true or something ordinary has been quietly overlooked. Cosmology has a hard-won humility about precisely this. The history of the subject is littered with towering certainties that melted under a second look. An extraordinary claim does not get to borrow confidence from the size of its own number. It has to earn that confidence by surviving the people who most want to prove it wrong. And the people who wanted to prove this one wrong were already sharpening their pencils. And if that were true, it would be one of the most staggering claims in the history of science. It would mean those faint, warm rings scattered across the oldest light we can see are not noise and not the seeds of our own galaxies, but the dying breath of black holes that burned out in a universe that ended before ours began. It would mean the question Hawking called meaningless, the one about what lies before the beginning, has an answer written across the entire sky, and the answer is a chain of universes with no first link. Either those circles are the fingerprints of a dead cosmos, or they are a pattern we wanted so badly to find that we found it in the static. The difference between those two sentences turned out to come down to a single, ferocious argument about statistics. And that argument is where we go next. The trouble with a claim this large is that the evidence for it is unbelievably small. So before we can weigh whether Penrose found a dead universe, we have to be precise about what a Hawking point is even supposed to look like. Down in the data, the theory makes a specific prediction, and specificity is what separates real science from a story. A Hawking point should not be a vague smudge. It should be a roughly circular region in the cosmic background where the temperature is slightly raised, hottest at the dead center and cooling off smoothly as you move outward, fading back into the ordinary glow at its edge. There is even a ceiling on how big these circles can be. Because of how far a signal could have spread in the early universe, a Hawking point should reach a maximum radius of about 2 degrees across the sky, which is roughly 4 times the width of the full moon. Around that warm disk, the theory expects faint concentric rings, regions of unusually low variation, like ripples frozen around a stone that fell in a previous world. That is a clean target, And in 2018, Penrose and his colleagues went hunting for it in earnest. They took the best maps we have of the cosmic background, from the European Planck satellite and from the older WMAP mission, and they searched for these warm, ringed, circular features. Finding a pattern is easy. Anyone can find shapes in noise, the way you find animals in clouds. The hard part, the only part that matters, is showing that the pattern appears more often than pure chance would produce. To do that, you compare the real sky against a large number of fake skies, simulated universes with none in them, generated to match everything we already understand about the cosmic background. If your special circles show up far more often in the real data than in the fakes, you may have found something. If they show up just as often in the fakes, you have found nothing but your own pattern-hungry eyes. Anne, Meissner, Nurewski, and Penrose ran their search against 1,000 simulated skies, and then, to be safe, against 9,000 more. And they reported that the warm, ringed features in the real cosmic background stood out at a confidence of 99.98%. In plain terms, they were claiming that the chance of seeing a signal this strong by accident was less than 2 in 10,000. By the loose standards of headlines, that is a discovery. The previous Aeon had left its fingerprints, and 4 physicists had lifted them off the sky. But this was not the first time Penrose had announced he could see the universe before ours. And the history of his earlier attempt is the reason so many cosmologists narrowed their eyes the moment the new paper appeared. Back in November of 2010, Penrose and the Armenian physicist Vahe Gurzadyan had made a related claim. Not warm disks that time, but concentric circles in the cosmic background where the temperature varied unusually little, rings of calm that they argued were the gravitational echoes of black holes colliding in the prior Aeon. They did not report it as a hint. They claimed a statistical significance of more than 6 standard deviations, which in physics is the threshold normally reserved for a confirmed discovery. The press obliged with the usual headlines about a universe before the Big Bang. And then, almost at once, the field answered. 3 separate teams of cosmic background analysts working independently took the same data and checked it, and they did not mince words. One paper came from Ingun Rehus and Hans Christian Eriksson. Another, published on the very same day, came from Adam Moss, Douglas Scott, and James Zibin under the blunt title, "No Evidence for Anomalously Low Variance Circles on the Sky." A third came from Amir Hajian, asking directly whether there were echoes from the pre-Big Bang universe, and concluding that there were not. All 3 reached the same verdict. The special circles were real, in the sense that they were there. They were not real, in the sense that mattered. The same circles, in the same abundance, showed up in plain simulated skies that contain no previous universe at all, no exotic physics, nothing but the ordinary random structure the standard model already predicts. Hajian found the claimed signals consistent at the level of 3 standard deviations with a perfectly ordinary inflationary sky. What had gone wrong is the same kind of mistake that haunts this entire field, and the physicist Sean Carroll wrote one of the clearest explanations of it. When Gurzadyan and Penrose built the fake skies they were comparing against, they had not properly captured what the real cosmic background is like. They effectively treated it as if its temperature varied randomly from point to point, like television static, when in truth the cosmic background is rich, lumpy, correlated structure, with broad warm and cool patches spread across the sky. By feeding their comparison the wrong kind of fake sky, one far too bland and featureless, they made the real sky's perfectly ordinary lumpiness look extraordinary by contrast. the test was rigged, without anyone meaning to rig it. When the rebutting teams generated honest simulations that fully reproduced the real correlated structure of the cosmic background, the circles appeared exactly as often as before. The message was blunt and a little humbling. You can find circles in the sky if you go looking for them. They are just what randomness produces. The pattern was real. The meaning was imaginary. And this is not a danger unique to Penrose. The whole field had been taught a hard lesson only a few years before by one of the most painful episodes in modern cosmology. In 2014, a team running an experiment called BICEP-2, observing the cosmic background from the South Pole, announced that they had detected a faint swirl pattern in the polarization of that ancient light, the long-sought fingerprint of gravitational waves from the first instant of inflation. It was hailed as one of the discoveries of the century. There was open talk of a Nobel Prize. And then, within months, the Planck team showed that the swirl could be explained almost entirely by dust in our own galaxy, scattered along the line of sight. The signal of creation turned out to be local grime. No one had been dishonest. They had simply underestimated how easily the foreground could mimic the thing they were hoping to see. The cosmic background is the most carefully studied light in existence, and it has fooled some of the best people alive. So when the 2018 paper landed with its 99.98%, the people who remembered both 2010 and 2014 did not celebrate. They went back to the data. The most decisive answer came the following year, in 2019, from two physicists at the University of British Columbia in Vancouver. Their names were Dylan Joe and Douglas Scott, and Scott had been one of the authors of the original 2010 rebuttal, so he came to it with a practiced eye. Their paper had a title that left no room for poetry: Re-evaluating evidence for Hawking, points in the cosmic microwave background. What Joe and Scott put their finger on was subtle, and it is the kind of thing that decides scientific arguments far more often than people realize. When you go searching for a warm circular feature, you do not know in advance how big the circle should be. So you try many sizes. You look for small rings and large rings and everything between. And here is the trap. The more sizes you allow yourself to search through, the more chances you give random noise to throw up something that looks impressive at one particular size. Think of it like scanning a long shoreline for a stone of a very specific shape. If you are allowed to call any stone a match, and you search a long enough beach, you will certainly find one, and it will mean nothing. If you then report only your best find and quote its rarity as though you had only ever looked at that one spot, you have fooled yourself. You have to account, honestly, for every size and every place you searched. Statisticians call this marginalizing over your search or correcting for the look everywhere effect. Joe and Scott redid the analysis while properly accounting for the full range of ring sizes that had been searched, and the towering 99.98% confidence fell out of the sky. Once you corrected for the look everywhere problem, the real excess of Hawking points sat at about 87%, a little more than one standard deviation. In the language of physics, that is not a signal. That is the kind of bump that washes in and out of data, sets all the time, and means nothing. Their conclusion was as flat as their title. There is no statistically significant evidence for Hawking points in the cosmic background. And that, you might think, is the end of it. The dead universe was a mirage after all. But here is what I find genuinely hard about this story. The thing that keeps it from being a simple tale of a great physicist fooling himself. Penrose did not concede. He and his collaborators have continued to argue that the features are there, refining the search, introducing new methods. In one follow-up, they leaned on a technique they called a sky twist, analyzing the actual data directly without leaning on simulations at all, and reported that the concentric structures depend sharply on the rings being truly circular rather than even slightly squashed, which is exactly what the theory predicts and what random noise should not care about. The fight did not resolve into a clean victory for either side. It hardened into a standoff between people who are all extremely good at this, looking at the same faint marks in the same ancient light, and disagreeing about whether anything is there. What would it actually take to settle this? That is where honesty lives in science. The lesson of the look everywhere effect is brutal and simple. A pattern found by sifting through data you already have is far weaker than a pattern predicted in advance and then confirmed in data you had never seen. The rings were, in a real sense, found by looking. What the theory needs now is a clean prediction, written down first and then tested against fresh and independent observations. Better data is on the way. A new generation of telescopes is now mapping the oldest light in still finer detail, measuring not only its temperature, but the subtle way it is polarized, the direction its waves are combed as they cross the sky. If warm rings of the predicted size and shape keep surfacing there in data gathered after the prediction was already on the record, and if they survive an honest accounting of every place and every size that was searched, then the argument shifts. If they wash out, the door quietly closes. But there is a deeper catch, and Penrose knows it better than anyone. Even a flawless detection of rings would not by itself prove that a universe came before ours, because the cosmos has more than one way to draw a circle. What would truly make the case is corroboration from a completely different direction. The erebons, the faint gravitational whisper of dark matter dying, an independent thread pointing at the very same story. One disputed signal is a curiosity. Two unrelated signals quietly agreeing would be something almost no one could wave away. We do not have the second thread. We barely have the first. And so the most honest sentence anyone can offer about the universe before the Big Bang is this: we have built a real door, found a few faint scratches on its surface, and have not yet been able to open it. Meanwhile, the theory underneath kept being built. As recently as 2025, Penrose and the physicist Christoph Meissner published a detailed treatment of the surface where one Aeon hands off to the next, the join they call the crossover 3 surface, working out in careful mathematics how energy and information might actually pass across the boundary between a dying universe and a newborn one. This is not the behavior of a man who has given up. Penrose is, as of this telling, in his 90s, a Nobel laureate who could rest on any number of laurels, and he is still trying to nail down the physics of the doorway. Whatever else you think of conformal cyclic cosmology, the commitment is real. There is something almost moving in it, an old man who proved the existence of singularities as a young one, spending his final decades insisting that the greatest singularity of all is not a wall, but a hinge. So where does that leave us, honestly? Not with a previous universe confirmed. The strongest independent analysis says the evidence is consistent with random chance, and in science that verdict carries enormous weight. But not with the idea killed either. The theory is internally coherent. It makes the kind of testable prediction that eternal inflation has always struggled to offer. And the disputed signal sits in a genuinely difficult place, in data so faint and so tangled that brilliant people cannot agree on what it shows. The honest answer to whether anything came before the Big Bang is not yes, and it is not no. The honest answer is that we have a serious theory, a contested set of marks in the oldest light there is, and we do not yet know. I find that more unsettling than a clean answer would be, a clean no would let you sleep. This leaves the door standing very slightly open. And before we ask what it means to live under a door left ajar, there is something we owe the rest of physics. Because Penrose is not the only one who has tried to see past the beginning. He is just the one who committed hardest to a test. There are other serious ideas about what the Big Bang really was, and to judge his fairly, you have to set it beside its rivals. Start with the gentlest of the rivals, the one that does not try to find a before at all, but instead dissolves the question from the inside. It belongs to Stephen Hawking, working with the American physicist James Hartle, and they published it in 1983. They called it the no boundary proposal, and it is the real source of Hawking's line about the South Pole. The idea uses a mathematical trick in which, as you approach the Big Bang, time gradually stops behaving like time and starts behaving like another direction of space. Run the clock backward toward the beginning, and the distinction between past and future softens, blurs, and finally vanishes, the way the lines of longitude on a globe all run together and lose their meaning exactly at the pole. There is no edge. There is no first moment with a blank wall behind it. The universe in this picture is finite in its past, but has no boundary, no sharp starting line. The same way the surface of the Earth is finite, but has no rim you could fall off. Ask what is south of the South Pole, and you are not hitting a wall. You are asking for a direction that has quietly ceased to exist. The no boundary proposal answers the question of what came before by showing, with real mathematics, that the question runs out of meaning before it runs into an answer. It is elegant and deep. Its weakness is that it is fiendishly hard to test. It makes statements about the overall shape and likelihood of universes, not about a specific freckle you could go and find in the sky. The second rival takes the opposite stance. It says there absolutely was a before, a real one, with a real clock ticking through it, and our Big Bang was a violent handoff from an earlier phase. This is the family of bounce cosmologies, and the most developed version grows out of an approach called loop quantum gravity, which tries to do the one thing Einstein's theory cannot. It tries to describe what happens when gravity becomes so strong that the smooth fabric of space-time itself breaks down. In ordinary general relativity, wind the universe back to the Big Bang, and the equations hit a singularity, a point where density and temperature shoot to infinity, and the mathematics simply stops working. Physicists do not actually believe in infinities. An infinity in your equations is almost always a sign that your theory has been pushed past the edge of what it can describe. Loop quantum cosmology proposes that space is not infinitely divisible, that at the smallest scales it comes in discrete grains, like a beach that looks smooth from a distance but is made of separate sand. And when you pack a universe down toward that grainy limit, something remarkable happens in the equations. Gravity, always an attractive force in our experience, flips. It becomes repulsive. The collapse halts and reverses. The physicist Martin Boyerwald showed, in 2001, that this framework could remove the Big Bang singularity altogether. A few years later, in 2006, Abhay Ashtekar, working with Tomasz Pawlowski and Parampreet Singh at Penn State, ran detailed numerical simulations of a simple universe through this regime and watched what happened. The universe did not plunge into a singularity and vanish, It contracted to an enormous but finite density, and then it bounced, rebounding into expansion. In this picture, our Big Bang was a big bounce. Before it lay a previous universe, a real one, contracting through the eons, squeezed down to the brink, and flung back outward into the cosmos we now inhabit. Unlike Penrose's Aeons, which connect only at a scaleless conformal boundary, the bounce is a genuine, physical event with a universe of ordinary matter and time on the far side of it. And the density at that turning point is its own kind of staggering. The bounce is thought to happen when the universe is squeezed down toward the natural limit where quantum gravity takes over, a density so far beyond anything that exists today that the numbers almost stop meaning anything. To put one handhold on it, a single teaspoon of matter packed that tightly would outweigh the entire observable universe. At that brink, in the loop quantum picture, space itself refuses to be compressed any further and shoves back, and the collapse becomes a rebound. It is a profoundly different vision from Penrose's, where his universes meet at a smooth boundary with every trace of scale wiped away. The bounce holds onto its scale and rides straight through the squeeze. Two utterly different stories about the same instant. One says the Big Bang was a perfect forgetting. The other says it was a violent rebound that carried everything across. The trouble, the same trouble that dogs almost every idea in this field, is that the bounce happened so deep in the past and at such extreme conditions that the signatures it might have left are subtle and contested, and the underlying theory of quantum gravity is itself still unfinished. The third rival is the one most people have actually heard of, even if they have heard it mangled. Eternal inflation grows out of the same inflationary physics we met earlier, the idea that the infant universe underwent a brief, violent stretching. The eternal version says that this stretching, once started, never fully stops everywhere at once. In most of the larger reality, space goes on inflating forever, and every so often a small region settles down and becomes a universe like ours, a bubble of calm in an endlessly boiling sea. In that picture, the before is not a previous universe in time, but the eternally inflating background out of which our bubble condensed. And there are endless other bubbles, endless other universes, most of them with different properties entirely. It is a vast and dizzying vision, and we will give it the full attention it deserves another time, because it raises its own strange questions about copies and probability. For tonight, the thing to notice is the criticism that has shadowed eternal inflation from the beginning. It is extraordinarily difficult, perhaps impossible, to test. The other bubbles are forever beyond our horizon. The theory may be true, but it struggles to tell us how we could ever know. There is a fourth idea worth a passing nod, because it sits closest to Penrose in spirit. In the early 2000s, the physicists Paul Steinhardt and Neil Turok proposed a genuinely cyclic universe built on ideas from string theory, in which our cosmos is one face of a higher dimensional structure that periodically collides with another, each collision igniting a new hot phase, a new beginning. It is cyclic, like Penrose's, but the mechanism is utterly different, and it leans on physics, colliding higher dimensional sheets called branes that remains speculative and incompletely understood. So line them up. The no-boundary proposal dissolves the question. The bounce replaces the singularity with a rebound from a previous universe. Eternal inflation drowns our universe in an endless sea of others. The colliding brain cycle rebuilds the cosmos from a higher dimensional crash, and conformal cyclic cosmology glues the cold death of one universe onto the hot birth of the next. 5 serious attempts by some of the finest minds in physics to say what the Big Bang really was. And here is the thing that, whatever you make of his rings, sets Penrose apart from all of them. He told you exactly where to look. He did not retreat into mathematics that can never be checked, or into other universes forever out of reach. He pointed at a specific kind of light, the cosmic background we have already mapped in exquisite detail, and he said, "If I am right, you will find warm, circular scars of a particular size and shape, right there, in data you already have. That is the rarest and most honorable thing a speculative theory can do. It makes itself vulnerable. It hands its critics the weapon. The evidence so far has not held up under that scrutiny. But the willingness to be tested at all is exactly why conformal cyclic cosmology deserves to be taken seriously, where so many grander, safer, untestable visions deserve mainly a shrug. A theory that can be proven wrong is worth more than a theory that can only be admired. Penrose built his to be shot at, which means the door he opened is a real door, not a painted one. And if there is even a chance that something stands on the other side of it, then the question stops being about statistics and the cosmic background and becomes about you, lying here in the dark, inside one link of a chain that may have no first link and no last. A cyclic universe is one of the oldest dreams in cosmology, and the dream has a graveyard behind it, which is what makes Penrose's version matter. Long before anyone could write down an equation, human beings sensed that time might move in circles. The ancient Greek Stoics believed the cosmos was periodically consumed in a great fire and then born again, an endless sequence of worlds, and they had a word for that conflagration. They called it ekpyrosis. That word did not stay buried in the past. The modern ekpyrotic model we touched on a moment ago, the colliding brain cycle, is named directly after the Stoic idea of a universe burned down to nothing and begun again. The oldest cyclic intuition in Western thought is hiding inside the title of a 21st century physics paper. And it was not only the Greeks. Hindu cosmology imagined the universe breathing in and out across colossal cycles, the days and nights of Brahma, ages called kalpas that ran to billions of years, creation and dissolution, turning over without end. Of all the pre-modern pictures of time, that one came strangely close to the true scale of the cosmos, far closer than the few thousand years most traditions allowed. In the 19th century, the philosopher Friedrich Nietzsche turned the same shape into a thought experiment he called eternal recurrence. The idea that everything that has ever happened will happen again and again exactly the same, forever. I am not claiming the ancients knew any physics. They did not. But there is something worth noticing in how stubbornly this shape keeps surfacing. The same circle drawn in the dark by cultures that never spoke to one another. Fire and rebirth. Dissolution and dawn. Modern cosmology spent the better part of a century insisting instead on a single line with 2 raw ends, one beginning and one death. And now, quietly, in Penrose's Aeons and the quantum bounce and the colliding brains, the circle is creeping back into serious science, dressed this time in tensors and satellite data. Penrose did not borrow it from the Stoics. He arrived at it through the geometry of infinity and the relentless logic of entropy. But he landed on a shape that human beings have been sketching for thousands of years. The idea of a universe that expands, collapses, and is reborn goes all the way back to Alexander Friedman, the same man who first found the expanding solutions in 1922. he noticed that his equations also allowed a universe that swelled and shrank in an endless rhythm, a cosmos with no true beginning, bouncing forever. It was a beautiful thought, and for a while it offered a way out of the uncomfortable idea of a single creation. But in 1934, the American physicist Richard Tolman did the careful thermodynamic bookkeeping, and what he found quietly killed the dream for the better part of a century. Tolman's problem was entropy, the same relentless disorder we met earlier. In a universe that collapses and bounces, the disorder built up in one cycle does not vanish at the bounce. It carries over into the next. So each cycle starts with more entropy than the one before, which means each cycle burns longer and grows larger than its predecessor. Run that forward, and the cycles swell without end. But run it backward, and the cycles shrink, getting shorter and smaller the further into the past you look, until they pinch down to nothing. In other words, even an eternally bouncing universe, when you account honestly for entropy, still has to have a first cycle. It still has a beginning. The endless rhythm does not escape the Big Bang. It just dresses it up. For decades, that single observation was enough to bury cyclic cosmology, and it is the trap every new cyclic theory has to climb out of. And this is the quiet genius of what Penrose did, the reason his version is not just the old oscillating universe in new clothes. Conformal cyclic cosmology has no collapse. There is no crunch, no contraction, no squeezing of matter back down to a point. Each aeon simply expands forever, diluting itself into the cold, massless smoothness we have described. And that smoothness is precisely a state of the gravitational field with its entropy wiped clean, the whale curvature back down at zero. The disorder that built up over the life of the Aeon, all the clumping and the chaos, gets swallowed into black holes, and the black holes carry it away as they evaporate, until what crosses the threshold into the next Aeon is once again pristine. Penrose's cycle does not accumulate entropy the way Tolman's did, because it never carries the old structure across. It launders the slate completely at every crossing. The thing that killed cyclic cosmology for 90 years, the relentless pile-up of disorder, is exactly the thing conformal cyclic cosmology is built to dodge. Whether the dodge truly works is still debated, but it is a real answer to the oldest objection, and that alone earns it a seat at the table. Now let that settle into something personal, because a universe with no first morning changes what it means to be here for any of it. Think about how we normally place ourselves in cosmic time. We say the universe is 13.8 billion years old, and we feel late to the party, as if most of the show already happened before we arrived. Or cosmologists note that the era of stars is a brief flicker, that the universe will spend almost its entire future in cold darkness. And so we are actually early, living inside the rare lit window near the beginning. Early or late. Those words assume there is a beginning to be early after, and an ending to be late before. They assume the line of time has two ends, and that your position on it can be measured against them. Conformal cyclic cosmology takes both ends away. If there is no first aeon and no last one, if the chain runs backward forever and forward forever, then there is no fixed point to measure your earliness or lateness against. You are not early. You are not late. You are simply inside one link of a chain with no clasp, and the question of where you sit in the whole of time becomes as meaningless as asking which grain of sand is the first one on an endless beach. and the scale of a single link is already past anything a human mind can hold. Our own Aeon, from its Big Bang to the final evaporation of the last black hole, will run for something like 10 to the 100th years. Set that against a human lifetime, and the comparison breaks. If you shrank the entire age of the universe so far, all 13.8 billion years, down to a single heartbeat, the full lifespan of our Aeon would still outlast every heartbeat of every human who has ever lived or ever will, repeated more times than there are atoms in your body. And that titanic span is one link. One. Behind it, in Penrose's picture, lies another just as long, and another behind that, with no first one to reach. The deep time does not bottom out. It just keeps going down. Now turn it around and point it at our own future, because this is the part that genuinely changes how the ending feels. In the standard picture, the heat death of the universe is the bleakest fact in science. Everything we are, everything that was ever built or loved or written, all of it slowly comes apart. The stars burn out, the black holes evaporate, and the cosmos settles into a cold, thin dark that never changes again, a dead end with no door. But in conformal cyclic cosmology, that same final fade is not an ending at all. It is a handoff. The cold, smooth, massless state our universe is drifting toward is exactly the state that the next Aeon will experience as its own hot, dense, brilliant beginning. Our heat death is somebody's Big Bang. The long darkness at the end of our universe is the first light of a universe we will never see and that will never know we existed. The candle does not simply burn out. It lights the next one as it dies, across a doorway it cannot look through. There is a real consolation in that, and I do not want to wave it away. It means the universe is not a one-shot event, flaring once into existence and guttering out forever. It means the dark at the end is fertile. But sit with the rest of it, because the consolation comes at a price I find almost unbearable to think about clearly. For our death to become the next universe's birth, our universe has to be smoothed completely flat. Every structure has to dissolve, every galaxy has to be torn apart, every black hole has to finish evaporating, every last lump of order has to be ironed out into the featureless, scaleless calm that the next Aeon needs as its pristine starting point. The crossover does not preserve us. The crossover requires our erasure. The smoothness the next universe inherits is purchased with the total forgetting of everything that was ever here. Let that settle, because it is the strangest grief in cosmology. It is not that we end. It is that we are required to leave nothing behind. The next Aeon does not inherit our history compressed into a footnote. It inherits a clean slate, and the cleanness of that slate is precisely the absence of us. In the standard heat death, at least the cold dark technically still contains the scattered ashes of what we were, the stray photons that once left our stars. In Penrose's version, even that record is conformally smoothed away into the blank perfection a Big Bang demands. The universe does not just forget us, it must forget us completely in order to begin again. The forgetting is not an accident, it is the engine. It helps, and it hurts, to make the previous Aeon concrete for a moment. Penrose's theory says every Aeon runs on the same laws of physics, the same gravity, the same speed of light, the same rules for how stars catch fire and how atoms lock together. But the laws are not the history. The details, the actual unfolding, are written by chance. And so each Aeon is its own story, never a copy of the one before it. which means the universe before ours was not a rerun of this one. It had its own scatter of galaxies, its own constellations that no eye in our cosmos will ever trace, its own particular sequence of stars igniting and dying across spans we have no names for. It may have had worlds. It may, for all the theory forbids it, have had watchers of its own, something that woke on a warm rock under an alien sun and looked up and wondered, in whatever way it wondered, the very thing you are wondering now. What came before us? And all of it, the galaxies and the worlds and the watchers, whatever rose and whatever was loved and whatever was lost, was smoothed flat and erased so thoroughly that the only thing that may have reached us is a faint scatter of warm rings we cannot even agree are real. An entire universe, every story it ever held, reduced in the end to an argument between physicists about circles in the static. And that is our future too. Whatever we are, whatever we make, whatever anyone here ever felt mattered enough to give a life to, is headed for the same smoothing. Not burned, not frozen in a museum, simply ironed out, conformally, into the blank calm the next universe will mistake for its own fresh morning. The previous Aeon does not grieve for itself. It cannot. There is no one left inside it to do the grieving. There is only us, briefly, looking backward, grieving on its behalf, and on our own, in advance. And here is where I have to come back, one more time, to the warm rings. Because there is, in Penrose's theory, one and only one thing that survives the crossing. Not life, not memory, not a single artifact of any civilization that ever rose in any Aeon. The only marks that bleed across the doorway are the death flashes of black holes, the concentrated bursts of Hawking radiation from the great drains at the centers of dead galaxies. The Hawking points. If our Aeon leaves anything at all for the universe that follows, it will not be our art or our names or the fact that anyone here ever loved anyone else. It will be a handful of faint, warm, concentric circles scattered across a sky belonging to beings who, if they exist, will look up at those rings and very probably decide they are nothing but random noise. The only message a universe can send across its own death is the signature of the places where its light fell in and could not get out. Even that, the one surviving trace, arrives unreadable. We argue right now over whether the previous universe left such marks in our sky, and we cannot tell. Whatever comes after us will face the same faint smudges and the same impossible argument, and will likely shrug, the way most of our own cosmologists shrug, and move on. You can ask whether any deeper information truly crosses over, whether there is some hidden channel that carries more than these scars. Penrose thinks there may be, and we will come to the strange particle he invented to carry it. But even in his most hopeful version, what passes through is not anything you would recognize as the contents of a world. It is not the universe before ours in any form we could read as a story. It is a smoothed out whisper, a faint imprint on the geometry, the cosmic equivalent of a pressure that shaped the next thing without ever telling it why. So which is it, this theory, a comfort or a horror? I have gone back and forth on it the entire time I have lived with the idea, and I think the honest answer is that it is both at once, and that the two cannot be separated. It offers you a universe that never truly ends, an endless chain of dawns, no final night. And it buys that endlessness with the absolute erasure of every dawn that came before. Immortality for the cosmos, oblivion for everything in it. The wheel turns forever, and turning is the same thing as forgetting. I find I cannot decide whether that should make me feel held by something vast and patient, or unbearably small inside it. Maybe that is the correct response. Maybe a theory about the death and rebirth of universes is supposed to leave you unsure whether to be soothed or afraid. And underneath all of it sits one question that even Penrose's elegant machinery cannot reach. Conformal cyclic cosmology can tell you in beautiful detail how the end of one aeon becomes the beginning of the next. It can show you the geometry of the crossover, the smoothing, the handoff of the warm rings. What it cannot tell you is why there is a next aeon at all, why the wheel turns rather than simply stopping at the cold dark and staying there forever, why a dying universe gives birth instead of merely ending. The theory describes the doorway with great care. It has nothing to say about why there is anything on the other side of it, rather than nothing. And that, I think, is the most honest place this idea can leave us. It pushes the great question back one step further than anyone had pushed it before, and then it runs out of road in exactly the same darkness as every theory that came before it. There was something before the Big Bang. Fine. Then what made that turn? And the turn before it? And the one before that? All the way down a staircase with no bottom. I keep circling that image, the staircase with no bottom, because it is where the comfort and the dread finally fuse into a single thing. Conformal cyclic cosmology does not answer the oldest question there is. Why is there something rather than nothing? It does not even try. What it does is move the question, push it back one aeon further than anyone had managed to push it, and then hand it back to you intact, exactly as heavy as it always was. And maybe that is the most any physics can ever do. Maybe every theory we will ever build just shifts the mystery one room deeper into the house and hands you a more beautiful version of the same locked door. There is a strange dignity in a theory honest enough to show you precisely where it runs out of answers. I find more peace in that than in the theories that pretend there is no edge, that wave a hand and say, the question is meaningless and you should stop asking it. Penrose does not tell you to stop asking. He builds you a longer staircase, lights it as far down as the mathematics will reach, and then stands beside you at the place where the light gives out, looking down into the same darkness that human beings have stood over and wondered about since long before any of us knew the universe had a size at all. There is one more piece of this that almost nobody talks about, a part of Penrose's theory so strange that even people who follow conformal cyclic cosmology tend to skip past it. It is the part where he had to invent an entirely new particle to make the whole thing work, and where that particle may be quietly decaying inside our own galaxy right now as you lie here. That is where we go to finish this. There is a hole in conformal cyclic cosmology that I have not mentioned yet, and the way Penrose chose to fill it is the strangest part of the entire theory. Remember that in the standard story, the faint ripples in the cosmic background, the seeds that grew into every galaxy, are usually explained by inflation, that brief, violent stretching of space in the first instant. But Penrose threw inflation out. His theory has no room for it. So he has a problem the standard model does not. If there was no inflation, what planted the seeds? What carved the tiny temperature variations into the newborn universe that would later grow into all the structure we see? To answer that, and to solve a second great mystery at the same time, Penrose reached for a particle that no one has ever detected and that he simply invented because the theory demanded it. That second mystery is dark matter, and the problem is genuinely old and embarrassing. It did not start with Penrose. It started in 1933, when a brilliant and abrasive Swiss-American astronomer named Fritz Zwicky studied a swarm of galaxies called the Coma Cluster and noticed that they were moving far too fast. The galaxies were whirling around one another at speeds that the gravity of all their visible matter could never hope to contain. By rights, the cluster should have flown apart long ago. Something unseen was holding it together, some great reservoir of mass that gave off no light at all. Zwicky called it Dunkel Materie, dark matter, and then the world mostly ignored him for 40 years. It took the careful work of the American astronomer Vera Rubin in the 1970s to make the problem impossible to dismiss. Rubin measured how fast stars orbit in the outer reaches of spiral galaxies, and she found something that should not have been possible. The stars at the edge were moving just as fast as the ones near the center, when everything we understood about gravity said they should be dawdling along far more slowly, the way the outer planets crawl around the sun while the inner ones race. The only way to explain it was to assume each galaxy is embedded in a vast, invisible halo of unseen mass, far outweighing all its stars and gas combined. We have spent the half-century since then trying to catch a single particle of the stuff. We have buried exquisitely sensitive detectors deep underground, shielded from every disturbance, waiting for the faint nudge of a dark matter particle drifting through. Decade after decade, the detectors have stayed silent. A quarter of the entire universe is made of something we can feel through its gravity and cannot so far see, touch, or catch. There is not even agreement that dark matter is a substance at all. A rival camp, following the Israeli physicist Mordechai Milgram, who put the idea forward in 1983, argues that perhaps there are no hidden particles whatsoever, and that instead our law of gravity itself goes subtly wrong out in the faint, slow reaches at the edges of galaxies. Adjust the rule, this view says, and the galaxies hold together with no unseen mass required at all. The argument between hidden matter and modified gravity has run for 4 decades, and it is still not settled. So when Penrose declares that dark matter is a definite particle, the erebon, with a definite mass, created at the dawn of each Aeon and decaying across its life, he is not patching a small gap in an otherwise finished picture. He is making one of the boldest possible calls on one of the largest open questions in all of science, and then tying its answer to the death and birth of entire universes. If he is right, the substance that holds every galaxy together is a relic of the cosmos before this one. If he is wrong in the crowded company of a great many failed guesses in a field that has been guessing for 90 years. Either way, the sheer reach of the claim is staggering. Most physicists treat dark matter as a puzzle to be solved inside this universe. Penrose treats it as a message left over from the last one. Most physicists assume dark matter is some very light, very shy particle, far smaller than anything in an atom. Penrose went in the exact opposite direction. He proposed that dark matter is made of a single kind of particle that he named the erebon, after Erebos, the primordial Greek god of darkness, born out of chaos at the start of the world. It is a fitting name for the most secretive thing in the cosmos. An erebon, in his scheme, is a scalar particle, meaning it has no spin, and it interacts with the rest of reality only through gravity, which is exactly why it would be invisible to every detector we have ever built, and why those patient underground experiments would never feel a thing. But the truly startling feature is its mass. Penrose argued that an erebon should weigh about 100,000th of a gram. That sounds tiny, until you realize we are talking about a single fundamental particle. 100,000th of a gram is roughly the mass of a grain of fine sand. It is about the Planck-mass, the natural unit of mass in quantum gravity, and it is some 19 orders of magnitude heavier than a proton. Picture that. Most hunts for dark matter are looking for something far lighter than an atom, and Penrose is suggesting each particle of it weighs as much as a speck you could see with the naked eye, a grain of sand's worth of mass packed into something more fundamental than anything in the periodic table. There is an even stranger thread tied to that enormous mass. Penrose has spent years arguing, separately from all of this, that gravity is what finally collapses the fuzzy, multiple possibility states of the quantum world into the single solid reality we experience, and that the trigger is mass. Big enough masses, in his view, measure themselves, snapping out of quantum haze into definite existence. An erebon, sitting right around the Planck-mass, would be heavy enough to live exactly on that boundary, a particle massive enough to behave almost like a classical object while remaining utterly fundamental. So in Penrose's universe, the dark matter is not only the seed of cosmic structure, it is poised at the very threshold where the quantum becomes real. He did not invent the erebon casually. He built it to stand at the crossing point of his deepest ideas. And here is where the erebon earns its place in this story, because of what Penrose says it does. In conformal cyclic cosmology, erebons are created near the dawn of each Aeon, and they are not stable. Each one carries a finite lifetime, long, far longer than the present age of the universe, but finite. And when an erebon finally decays, it does not produce light or ordinary particles. It dumps all of its energy, the entire mass of a grain of sand converted directly into energy, into a single sharp burst of gravitational waves, a ripple in space-time itself. Now multiply that across an entire universe full of dark matter, decaying steadily across the whole life of an Aeon, each decay sending out its little gravitational shock. Penrose's claim is that this storm of gravitational impulses is what seeds the structure of the universe. It is the erebons, decaying through the previous Aeon and carrying their effect across the crossover, that plant the ripples in the new cosmic background, the ripples that grow into galaxies. In other words, dark matter is not just some inert scaffolding holding galaxies together. In this picture, dark matter is the messenger. It is the channel through which one universe shapes the next, the hand of the dead Aeon reaching across the doorway to press the first faint patterns into the universe being born. Sit with what that means about the present moment. If Penrose is right, the dark matter threaded all through our own galaxy, the invisible mass we know is here but cannot touch, is made of these erebons. And because they have a finite lifetime, they are decaying right now. As you lie here, somewhere out in the dark halo around the Milky Way, an erebon is reaching the end of its long existence and releasing a grain of sand's worth of mass as a silent pulse of gravitational waves that washes through the galaxy, through the solar system, through this room, through you, and onward. The dark matter is not eternal in this theory. It is slowly, particle by particle, disappearing. And every disappearance is a tiny rehearsal of the deeper story, energy released from matter, structure carried outward on ripples in space, the long handoff already quietly underway. Penrose, being Penrose, did not leave this as a poetic flourish. In 2017, he published a short paper with a deliberately provocative title, suggesting that the gravitational wave detectors we have already built might be picking up erebon decays without realizing it. The LIGO observatories, the instruments that first detected gravitational waves from colliding black holes, run as a pair, one in Hanford, Washington, and one in Livingston, Louisiana, about 3,000 kilometers apart. Penrose pointed out that a real erebon decay out in the galaxy would hit both detectors with a characteristic time delay set by the direction it came from, and so would show up as correlated noise between the two sites, the kind of thing analysts normally throw away as meaningless interference. He called erebons a reasonably robust implication of his theory, and he proposed an almost cheekily simple test. Pick a nearby galaxy, say Andromeda. Look in the discarded detector noise for correlated pulses, arriving with exactly the time delay that points back at it. If the dark matter there is decaying, the ghost of it should be sitting in the data we have been ignoring. It is a beautiful, bold, testable idea, and so far, it has not held up. When other physicists worked out how strong the gravitational wave background from decaying erebons should actually be, the answer was that it falls far below what LIGO could ever hope to detect by a wide margin, and the specific correlated noise Penrose pointed to has not survived scrutiny, with the detector teams concluding it is not a real external signal at all. The cosmologist Andrew Ponson, watching all of this from University College London, summed up the awkward position cleanly. The original analysis of the rings, he noted, was quite badly flawed, and the LIGO noise does not appear to be erebon decay either. And yet, in the same breath, he called conformal cyclic cosmology a beautiful theory that deserves a lot of attention. That tension is the honest state of the whole enterprise, a theory too elegant to dismiss, attached to evidence too weak to trust. Penrose himself remains undaunted, saying he is hopeful that future, more sensitive detectors might yet catch the gravitational whisper of dark matter dying in distant galaxies. So circle all the way back to the thumbnail promise, to the question that pulled you in. What came before the Big Bang? In Penrose's answer, the thing that came before did not simply end and vanish. A piece of it may still be here. The dark matter that outweighs everything you can see, the invisible mass that built the galaxy you live in, could be the surviving substance of the order before this one, slowly decaying inside our own cosmos, and in its dying, already laying down the seeds for the cosmos that comes after. The universe before ours would not be a closed chapter sealed behind an unreachable wall. It would be the rules we live inside, the seeds we grew from, and the silent rain of gravitational waves passing through us in the dark. Not gone, transformed, and still at work. So come back, one last time, to where we started, to the flat certainty in every textbook, the one Stephen Hawking liked to deliver with a small smile. There is no before. Asking what came before the Big Bang is like asking what lies south of the South Pole. The question is empty. The door is not locked, because there is no door. There is only the edge where the question runs out. I do not think you can listen to all of this and still hear that the same way. Maybe Penrose is wrong. The strongest independent analysis says his rings are most likely noise. His erebons have not shown themselves. His dead universe remains, for now, a beautiful, unproven thing. But notice what he did. Regardless of whether the data ever vindicates him, he took a question that the greatest minds of the last century had agreed was meaningless, a question you were supposed to be embarrassed to ask, and he turned it into a technical problem with equations and predictions and a search through real data. He dragged it back from philosophy into physics. He made what came before the Big Bang into something you could, in principle, go and look for. That alone changes the texture of the silence. The question is no longer obviously empty. It is merely unanswered. And those are not the same thing. There is a way of seeing this that I keep returning to in the quiet hours. If Penrose is right, the universe is built to forget. Every aeon ends by smoothing itself flat, erasing all the structure it ever held, handing a blank and perfect slate to the cosmos that follows. Forgetting is not a flaw in the design. Forgetting is the mechanism. It is how the wheel turns. And yet, inside each of these vast forgetful cycles, for a brief lit window between the dark before and the dark after, the universe assembles a little matter into beings who do the one thing the cosmos as a whole cannot. We remember. We look backward. We lie in the dark and try to see through a doorway that was specifically built so that nothing could be seen through it. That is what you are doing right now, at the end of a long day, on a small, warm world, trying to picture a universe that died before yours was born. You are the part of the cosmos that refuses to forget. You are matter that woke up and started asking about its own beginning. And this is the last time I will say the name, Hawking points. When we started, they were a curiosity, a set of warm rings a Nobel laureate claimed to have found. By now, you know they may be nothing at all. Just the shapes randomness throws up when a hopeful mind goes looking. But I have come to think that is almost the most human thing in this entire story. Faced with a doorway built for forgetting, we did not accept the silence. We searched the oldest light in existence for a message, for any sign that what came before us left something behind. The rings may be real. The rings may be a mirage we wanted so badly that we found it in the static. Either way, the searching is the point. A Hawking point, in the end, is what longing looks like when you write it down in the language of statistics. It is us, refusing to believe that the door swings only one way. We will probably never know. Not in your lifetime. Maybe not in any. The data is too faint. The universe too good at covering its tracks. The question too close to the edge of what physics can reach. And there is a strange peace in that, if you let yourself feel it. You do not have to solve it tonight. You do not have to decide whether the cosmos remembers or forgets, whether there was a universe before this one, or only the clean, blank edge where time begins. You only have to lie here, inside this single bright link of a chain that may have no ends, and let the oldest light there is keep arriving. Because it is arriving. Right now, the faint glow we have talked about all night is falling on you, the same way it falls on everything, everywhere, all the time. It set out when the universe was young and has been crossing the dark for almost 14 billion years to reach this room. Some of that light, if Penrose is right, carries the faintest fingerprint of a world that ended before the beginning. Most of it carries only itself. You cannot tell the difference, and tonight it does not matter which. The universe forgot how large it was. In the forgetting, it found room to begin again, and the light from before the beginning is still falling, soft and cold and patient, across the back of your closing eyes.